Welcome to my second talk about minimizing the Helfrich energy with geometric measure theory. Last time we've spoken about the variation framework of geometric measure theory for this problem. And today I'd like to tell you a bit about lower semi-continuity. Okay, just to repeat it, what is our actual problem that we want to solve or which we want to examine? We have a given sigma, some manifold, and we're taking a look at emergence from this sigma into R3. And we want to minimize under the class of these emergence this Helfrich energy over here. Just as a reminder, h is the mean curvature, h0 is a scalar parameter, and we want to calculate the L2 difference between these two guys, and we want to minimize this under given constraints. What are our constraints? We want to prescribe the area and the enclosed volume of F. And we're looking for the smallest F, also small in the sense that the Helfrich energy has to be small for this F in this class. So the smallest Helfrich energy. Okay, what we've already done is we have rewritten a minimizing sequence as a minimizing sequence in a varifold sense. So corresponding to every F, we find an oriented varifold, and we've already taken a look at that these guys actually satisfy a compactness criterion by Hutchinson. So that indeed we have a limit. Okay, now we have a limit. Let's call this limit V. And we have a minimizing sequence. So lower semi-continuity would mean this kind of inequality, this kind of estimate. And the question is, do we actually have such an estimate? Usually one would expect such an estimate to hold true every sequence of oriented varifolds which converge. But maybe this is not true here. As a reminder, this is a definition of measure convergence. So you just integrate over a test function phi, which is continuous with compact support, over your radon measure Vk, and this one should converge to the limit. Okay. There's an easier case. Let's take a closer look at the Willmore energy, which is basically just h0, so the spontaneous curvature to be 0. So imagine you do not have this term. What can we say then? A usual trick, so the first idea is to rewrite this Willmore energy as this guy over here. You can do this by standard Hilbert space techniques, and just some density of continuous functions with compact supports in L2. Okay, but to do this, your integrand has to be some form of square. So this square here is actually essential for this. Otherwise, this would not work. Okay, one might think, yeah, okay, in the Helfrich energy, there's a square as well. But if you write it down explicitly for the oriented varifolds, we have the following problem. We have two squares. We have one square here and one square here. And they are added. So in total, it is not a square anymore. So that means this first trick here is not applicable. Okay, one might think, okay, just because one proof does not work, maybe if we can find another one. Unfortunately, in general, this is not true. Carsten Grosse-Braukmann in 1993 actually found a counterexample for this lower semi-continuity estimate. He constructed a family of constant mean curvature surfaces which all have constant mean curvature 1. And they are dependent on some parameters. And if you just let one of these parameters go to the limit, then these constant mean curvature surfaces converge to a plane with double density. So what basically happens is that these gray parts here become bigger and bigger, and this white part here is where there's just an empty space, becomes smaller and smaller, and also these guys here become flatter and flatter. So that in the limit you have a plane with double density. Okay, what does it mean for the Helfrich energy? Just imagine your spontaneous curvature would be 1. Then the Helfrich energy of these constant mean curvature surfaces would be 0, and for the plane it would be non-zero. So this is exactly the opposite of the lower semi-continuity estimate. Of course, this counterexample here is not really our minimization problem. First of all, Carsten Grosse-Braukmann's counterexample here is infinitely big. So it is constructed to be a periodic kind of surface. The other part is that we actually, the second fundamental form, the L2 norm of the second fundamental form of these guys here will explode, which is not the case with us because we have control over the topology. So this cannot happen, which also means we have still some chance for our problem that we can establish such an estimate. Okay. And indeed, there is hope. I've shown a little theorem in 2019, which basically says the following. Let's go back to our minimizing problem here. So now we have a minimizing sequence Fm, and these Fms correspond to oriented varifolds Vm, and they converge to a limit varifold V. And since we're working with these, since these Vms have a smooth immersion in the background, we can actually show that the minimizing sequence itself satisfies a lower semi-continuity estimate. So, okay. That would also mean that this V0 is kind of minimal. How do you prove that? Let me give you at least an idea on how to proceed. So we want to use our initial idea for the Willmore energy. So we can rewrite this square, this L2 norm, as a supremum. But this will only work if we have density 1 surfaces. So the idea is to show that the limit actually is a union of density 1 surfaces. In other words, of graphs, locally at least. So if we have shown this, we can actually show lower semi-continuity for one such graph, for example for the red one. And then afterwards, we combine all of these guys together to obtain a global lower semi-continuity estimate for the whole sequence. Okay, this first decoupling in graphs, I'd like to tell you this works in a bit more detail. And what is here in the background is the graphical decomposition lemma, which was initially introduced by Leon Simon and later used and refined by Rainer Schätzle, Sebastian Schigola, and other people. This graphical decomposition lemma basically says the following. These AMs here is the second fundamental form of our minimizing sequence Vm or Fm. And if the L2 norm of this guy, these guys is smaller than epsilon 0, independent of m, essentially. And this epsilon 0 is small but bigger than 0 and fixated. Then you can show that the limit varifold is around a fixated point x, so you're allowed to choose this rho to be small. Then we can actually show that the limit varifold is a union of C1 alpha graphs, of finitely many C1 alpha graphs, around this fixated point x, with some smaller radius. Okay, why is this now useful? If you take a closer look at this proof of this guy, you get the following. First, you decouple your minimizing sequence into density 1 surfaces, not necessarily graphs. They may have some pimples, as they are called in Lee and Simon's paper. So, for example, this little red bump over here, or this blue bump over here. But in the limit, they will stretch out. What I mean with that, this density 1 blue surface here will converge in a measure theoretic sense to this blue surface. This red guy will converge to this red guy. This green guy will converge to this green guy. So what we have actually shown is that the decoupled minimizing sequence converges to a decoupling in the limit. And this is exactly what we need, because what we have now is we have here density 1 varifold, which converges to a density 1 varifold. So we do not have two square terms anymore in our Kahneman-Helfrich energy. And this is exactly what we need. So this is the Kahneman-Helfrich energy for one of these graphs, mu I. So mu I is now, for example, this red line over here. And the mu mi's converge in the measure sense to this guy. And then we can use our density characterization for L2 norms and find a smooth function with compact support such that we can estimate this guy to this guy over here plus some error term, which is arbitrarily small. So usually one would write a supremum over here and neglect this error term, and the supremum would go over all of these phi's. But of course we want to work with one of those phi's, so this estimate is more appropriate. Okay, why is this now good? This is good because geometric measure theory essentially gives us that this guy here is the limit of this guy. So just by having that the mu mi's converge in the varifold sense to the mu I actually gives you this equality over here. And now we're in business, because now we can just manipulate this term over here by Cauchy-Schwarz's inequality. And this will yield in the first term over here the Kahneman-Helfrich energy of the sequence mu mi. So essentially exactly what we want, times the L2 norm of phi. But since phi square is again smooth or continuous with compact support, this guy will actually converge. And it will converge to the same term, just without an m. And this here, this guy, is chosen to be smaller than 1. So it will just drop out. And then essentially what we have is the Kahneman-Helfrich energy of one graph is smaller than the approximation of this graph from the minimizing sequence from the Kahneman-Helfrich energy of this approximator, plus some error term which can now be neglected because The left-hand side and the right-hand side do not depend on the test function phi anymore. So what we've now established is low semi-continuity for one such graph. And now you have to just build everything back together. You take the union over all of these graphs, and then you basically get your lower semi-continuity result, which I've mentioned in the beginning. Okay. Enough with the proof. Let me tell you about some other approaches to this low semi-continuity problem. In 1997, Deladio already looked at it and tried to solve this problem in the setting of so-called Gauss graphs. Gauss graphs are also part of geometric measure theory. There are certain type of currents, but he had to essentially have some prerequisites which are not so clear in general. For example, you need some regularity in the limit, some density assumptions, which are also they're not very. The picture was still very incomplete. This approach, which was a few weeks ago actually, was improved by Kubin, Lusardi, and Morandotti. And they used some convexity. They showed some convexity for the kind of Helfrich energy in the right setting, and then used some of Hutchinson's results about measure function pairs, and were actually able to show more than the Deladio originally did. So this is okay. Then there's another approach, the parametric approach that I already talked about in the last video, in the end of the last video. Andrea Mondino and Christian Scharrer were able to show lower semi-continuity. Essentially, with our problem, just the topology, so the sigma, this big sigma, has to be the sphere. And they showed it with this parametric approach by Tristan Rivière. But just check out Christian Scharrer's video. He will talk about this, and he will explain it to you. And then there's another result in the case of varifolds by Caterina Brazza, Luca Lusardi, and Ulysses Stefanelli. And they were able to show lower semi-continuity essentially for a certain type of Canham-Helfrich energy. If you add some other terms to it, and then they were able to show lower semi-continuity for some of the parameters. But for this, just check out Caterina Brazza's video. She will explain this. Okay. Finally, some take-home messages. Actually, just one take-home message. Just think about what we've done today. Usually, in these kinds of minimizing problems, you first show lower semi-continuity, and then you're able to show regularity. By the minimizing property, you can vary your limit a bit, then you get an equation, and then you can do all kinds of stuff. Here, on the other hand, we've shown regularity even before we had lower semi-continuity. Sometimes this is possible and necessary to do. Okay, with that, I'd like to thank you for your attention, and have a nice day, and bye-bye.